Hi guys, hope you are all doing great. My name is Ernest. Today we're going to look at one of the topic under nuclear fission and fusion, and that is the concept of nuclear fission. Now, this specific concept is going to assist us understand and appreciate one of the applications of this specific process in trying to produce, of course, the nuclear energy that we already having experience with in some of our areas. So in this case, it's also going to assist us in trying to find ways in which we can be able to do research and come up with new ways in which we can be able to assist us, of course, make life better. So in this case, for today, I'm going to use some of the illustrations that we have already discussed on the concept of binding energy, so that we can be able to appreciate the relationship between binding energy and this process that is known as nuclear fission. So without further ado, thank you and welcome. So as I've said, today we're going to look at this specific process that is known as nuclear fusion. And if I may give a slight relationship that is going to assist us try to figure out what this specific process entails. Under the concept of enthalpy that we discussed in one of our videos, I said there's a process of bond formation. And of course, there's a process of bond breaking whenever we're trying to talk about maybe formation of specific compounds, or maybe just joining together of different atoms to form a compound. It entails the concept of either absorption or release of energy. So for bond formation, we're going to see that this one entails the release of energy, while bond breaking, this one involves the taking in of energy. Now in this case, the interaction between this specific concept of energy and the bonds is going to assist us understand the concept of the bond, the binding energy that we had given in one of our videos, introduction videos for nuclear fission and fusion. Now the concept of binding energy comes from the concept that inside the subatomic or the subatomic particles that we have inside an atom, we have the nucleus. And the nucleus contains protons and neutrons, basically, which are positively charged, and the neutron. Therefore, to keep this one together or form the nucleus generally requires what we call binding, or it involves binding energy. Now, this specific concept of binding energy is the one that is going to determine the stability of the nucleus. So therefore, if we try to do maybe calculation of try to find or quantify this specific energy, it's going to give us a relationship between the stability of different atoms. We're going to see that eventually for stable atoms, there's a relationship that exists in a sense that the higher the binding energy, the more stable the nucleus of an atom. So therefore, stability means that it's not going to either break or maybe basically try to break apart. And therefore, that nucleus is going to be referred to as stable. Now, the concept of nuclear fission came from some of the observation that was done around 1939. So this is a 20th century experiment that was done, whereby it was observed that if this specific element, we have talked about the concept of mass, energy, and atomic mass and of an element. Now, if we are on the mass of an element, or the concept of atomic mass of an element by representation of this specific, I hope that we understand that relationship. So I'm going to give this element uranium-235, and this is 92, of course. Now, it was observed that this specific element, if it was bombarded with a neutron, this is a neutron from the nucleus. If it was bombarded with a neutron, then it was observed that this specific element splits into two fragments. Let me call these fragments X and Y. And this was, of course, accompanied by the release of energy. And the daughter fragments that were achieved from this one tended to display more stability, of course, as from this concept that I've talked about. So in this case, this process results in the formation of products and energy, and in essence, the end process is going to result in a formation of a more stable element. So therefore, from this specific example, this particular uranium, therefore we're going to refer to it as the, the parent element that is going to split due to interaction between that element and the neutron in order to form X and the Y, which I've referred to as the daughter. This is a daughter nucleus, and this is another daughter nucleus, and together we can refer to them as a daughter nuclei, and the release of energy that we're going to see later. So in this case, as we have said, whenever we're going to split this specific nucleus, the constituents are going to be, of course, result as a product. Therefore, we're going to achieve also the release of some of the neutrons that exist inside the nucleus. Therefore, we're going to see this in a product sense by representation using the nuclear reaction equation that I'm going to give later in our discussion. So in this case, I want us to look at one of the examples that I've said about this specific concept of nuclear fission, and try to see how that one figuratively can be able to be represented. So from our illustration, we can see that there is an interaction between a neutron and uranium-235, which I referred to as a radioisotope. So basically, from our periodic table, we're going to meet a range of elements, which of course have got an unstable combination of the neutrons and the protons, as we have said about the concept of binding energy. So in this case, we're going to see that this specific unstable combination is going to result in the formation of a fusion of this radioisotope. So in this case, if it is bombarded with a neutron, it's going to split into the constituent neutrons that are basically inside there. But we're going to see that how however, even if it splits, it's going to be quantified in a way in form of an equation. So this is going to split into two daughter nuclei. The first one is cesium, that we have represented as such an Rb92, and which is going to be accompanied by this neutron and this one. So basically, we're going to see that apart from the daughter nuclei which are formed, there are other neutrons which are going to be released, and this one are going to initiate further a reaction which is going to result in a chain event. So in this case, if you try to look at one of the examples still for illustration 2, we're going to see that the same process is going to take place whereby uranium is bombarded with a neutron, and then it forms an unstable intermediary or an intermediate that is a uranium-236-92, which basically disintegrates or just undergoes fission to form daughter nuclei for krypton-92 and barium-141. So this will be accompanied by the release of 3 neutrons, which are basically represented as such. So we're going to see that we can be able to represent this chain event, or maybe the particular nuclear reaction in form of an equation. And it's basically going to be shown that it's going to obey the law for conservation of mass, which is analogous, of course, to the reacting volumes in stoichiometric analysis that we looked about. So in this case, I'm going to give an illustration for this specific equation to show how this interaction between the neutrons and the uranium-235 result in the formation of these 3 specific products and the release of energy. So from this above reaction, I've shown that uranium-235 in form of an equation is interacting on the product side, on the reactant side. If we try to assume that this is a stoichiometric equation, then we're going to see that we are going to have a uranium-235 that is interacting with a neutron, and this results in the formation of this specific resulting product and the release of energy. So therefore, we're going to have krypton-90 plus barium-143 and 3 neutrons. So basically, if we try to look at the stoichiometry of this, or maybe the mass numbers on the product and the reactant side, as I've illustrated. So I'm going to use this specific term loosely as such. So this, if we try to look at the product and the reactant side, we're going to see that the summation of these specific numbers is equal to the summation of this range of these numbers, whereby we can just do a math. This is 236 on the reactant side, and this is 233 plus 1 plus 1 plus 1. So this is going to give us 236, which basically is equivalent to this. And on this lower side we have 92, so this is 36 plus 56. This is going to be 92. Sorry for that. That is going to be 92. So basically, if we try to look at the mass numbers and the atomic numbers, they are going to give us a balancing equation that can be represented as such. And that, of course, gives us an impression that this specific process that is taking place obeys the laws of conservation of mass. And therefore, we're going to see that this release of energy is going to be illustrated in different ways. So the formation of this daughter nuclei that we have talked about, and in any case, if they are unstable, then they are going to undergo some of the processes that we have already observed in radioactivity in order to form stable ones. Perhaps in the release of beta gamma or the alpha particles in order to form stable ones. Now, as I've said, this process of nuclear fission is extremely important for us, in a sense that, of course, it assists in the process of attaining energy from the nuclear power plant, and of course, which is a basis for the clean energy that we have already seen being applied in some of our areas. So in this case, this is going to assist us in trying to differentiate between the process of nuclear fission and nuclear fusion. Now that we have understood the concept of binding energy and this one, now our last discussion will of course try to cement on what we have already discussed, so that in any case we come across this kind of a process that is taking place, or maybe we are being required to find the product of this and we have been given that it is interacting or maybe producing a basic number of neutrons, then we can be able to do that or solve that and maybe quantify it from the stoichiometric equation that I've talked about. Of course, we're going to look at the concept of a mass defect and the Einstein's energy relationship in this one of our additional videos after we have discussed the concept of nuclear fusion. Now, in this case, I hope that we have already taken a concept or two from what we have discussed, and let's catch up in our next video. So bye. Thank you. God bless.